Hello and welcome back, everyone. Moving on to section 1.5, talking about determinants, eigenvalues, and eigenvectors today. These are three kind of slightly advanced subjects in linear algebra, but they do show up in the study of multivariable calculus, especially determinants. So we'll make sure to cover them nice and good today. So let's just talk about this formula for the inverse of a 2 by 2 matrix right away, right? If we have A, B, C, D, and we want to invert that matrix, we get this term out front, 1 divided by AD minus BC. And so you find out very quickly that if the quantity AD minus BC is not equal to 0, then an inverse exists. And more precisely, if AD minus BC is equal to 0, then an inverse cannot exist. Okay, so this quantity, AD minus BC, must be pretty special in terms of the 2 by 2 matrix, special in the sense that we care when it's maybe not equal to 0 or when it is equal to 0, because that uniquely determines whether or not the inverse exists. There are going to be situations in which the inverse may not exist. And jumping to conclusions a little bit, I just want to mention that this AD minus BC, at least in the context of 2 by 2 matrices, is the quantity that we call the determinant. Quite possibly because it determines if the inverse exists. I'm not entirely sure the etymology on it, but we do call it the determinant. Let's look at a linear function, maybe f of xy is x plus y, 2x minus y, and let's ask ourselves, what does our function do? Put that in quotes, like how does it modify the unit cube, or in this case, I guess the unit square because we're in 2 dimensions, but some sort of unit box in whatever number of dimensions our function maps. So we start with the unit square and we ask ourselves, what does it look like under the action of f? If we put this square inside of f, well, what happens is the kind of the y-axis portion of the unit square. Now this happens to be the vector 0, 1, right? That's the vector pointing in the y direction, and then you've got this x directional vector, which happens to be the vector 1, 0. You can find out just where those vectors end up underneath the action of f just by plugging them into f, right? So if I go ahead and plug 1, 0 into f, I'm plugging a 1 in for x, 1 in for x, a 0 in for y, and a 0 in for y. You find out you have the vector 1, 2, which is the vector drawn up here, right? This is the vector 1, 2. Do the same thing with the vector 0, 1 for y, so you put a 0 in for x and a 1 in for y, a 0 in for x and a 1 in for y. You get the vector 1, -1, and that's what we've drawn down here, the vector 1, -1. And then of course you can complete the parallelogram that ends up being spanned by those 2 vectors. Okay, so this is what the unit square maps under if you plug it into f. And we can ask a very important question about this unit square, or the image of the unit square, this parallelogram. Important question: does it tile, like if I were physically laying tiles in this shape, right? If I have a kitchen that I would like to tile and I'm given a bunch of these shapes, does it tile the entire plane? Right? Could I fill out the entire plane if I had infinitely many of these parallelograms? And of course the answer here is yes, right? I could just get my second parallelogram here, my third parallelogram here, fourth, fifth, sixth, and so on. And these parallelograms will tile all of space if I allow myself to place future parallelogram tiles around the first one. And so that's kind of an important property for f to have, is that it maps the unit square into something which can tile all of the plane. It turns out that's going to correspond precisely into whether or not f inverse exists. And it corresponds to that because for the inverse to exist, you could take any point in the output, right? This is some point in the output, and you could find out that it takes 1, 2, 3 copies of the y-directional output and then a single copy of the x-directional output to recover that point. And that information is enough to declare where the point came from, right? The point came from 1, 2, 3 y copies and 1 x copy. So it ended up coming from this point, or this point in the plane 1, 3. So that's enough to give you that inverse map once you know you can tile the plane, but there are going to be situations in which you cannot tile the plane. Let's look at this situation. Linear function x minus 3y, -2x plus 6y. When we have this situation, well, our x vector 1, 0, if I plug that vector in, 1, 0, 1, 0, I end up with the output 1, -2. And if I put the y vector in, the y vector being 0, 1, I'm going to put a 0 in for x and a 1 in for y, I end up with the vector -3, 6. If I plot the vector -3, 6, I can plot it up here. And if I plot the vector 1, -2, I can plot it down here. We see that the parallelogram, right, if I were to kind of try to construct a parallelogram out of those two vectors, they're parallel, well, they're pointing in opposite directions, but they're still parallel. And in some ways, there is no parallelogram. Or equivalently, it's infinitely thin. However you want to think about that parallelogram, either infinitely thin or there is none, and can therefore not tile the entire plane. There's no way for me to grab a second copy of this line and place it right next to itself to eventually recover the entire plane. It's infinitely thin, so I would need kind of more than infinitely many straight lines to get the entire plane. So it turns out that you can't tile the entire plane, and equivalently, this means that F inverse cannot exist. So that's really what the determinant's going to hint at, because we have this lovely notion of tiling or not tiling in the later case. And the determinant is some quantity that measures how easily tiling can happen. And in reality, the determinant will measure this area. But of course, in higher dimensions, you can get the volume or the hypervolume. Okay, so there's, in 4 dimensions, there's still some 4-dimensional version of an object tiling space. You can think about area basically as how much space does one tile take up. And so, or even volume, right? If I wanted to not really tile, but fill a room with boxes, the volume of a box is how much space does one box take up. And so in higher dimensions, that's what you get. You get the equivalent of boxes filling space. That's your tiling equivalent. And the determinant's going to quantify that with a non-zero value. Okay, so here I have the actual definition of the determinant. The determinant is of a multi-dimensional linear function, f, denoted by det f, is the signed n volume of the image of the unit n cube. That is a whole bunch of garbage that is basically trying to quantify what I've already described. It's the area of that output parallelogram, but in higher dimensions, it may be a box or a 4-dimensional box and so on. Now this word signed is a little bit important. Why signed? Now it's not too important that the value is necessarily signed for now. We're going to see in multivariable calculus, there's a good reason for it to be signed. But for now, we're going to just assign it this sign, which may be positive or negative, and we only care about when it's equal to 0 for not being invertible. So where does the sign come from? The sign associated to the determinant is -1 to the k power. So it's going to be plus or minus 1, because -1 to the first power is -1, -1 to the second power is 1, and then it flips back and forth between 1 and -1. What is this number k? K is the number of edges that must be exchanged or flipped to preserve the original orientation of the unit n cube. That also sounds kind of strange. Let me describe what I mean by that up here with our earlier example of the determinant. Notice how the y direction is to the, let's say it's in the counterclockwise direction to x, right? So the x direction is horizontal, the y direction is vertical. That's pretty normal. But in particular, the y direction we care about is in the counterclockwise direction from x. If we look at the image under f, now the y direction is in the clockwise direction. So a flip has occurred. Flip or exchange, you can think about basically I've swapped the x and the y directions in terms of my orientation. So the fact that the y direction and the x direction kind of exchanged their orientation here, one flip has occurred, that's going to mean that the determinant will be negative because we've had one flip. If you end up with 2 flips, it makes the determinant positive again. And it turns out the reason why 2 flips would make it positive, even in higher dimensions, is that it causes everything to be rotationally equivalent to the original case, where if you provide a single flip, then it's never going to be rotationally equivalent. It's like there's a notion of clockwise-ness and counterclockwise-ness in any number of dimensions, and this is basically how we quantify that, the number of flips on the edges of the n cube. Okay, so you can also talk about the determinant of a matrix. Just as up here, I gave the determinant of a linear function, but the matrix will just be the same as the linear function. It's just defined to be the determinant of the linear function, which the matrix represents. So let's look at a couple examples just where I've directly plotted functions, so you can get an idea of what the determinant should be. This is the same function we analyzed earlier, x plus y, 2x minus y. You see that the y direction ends up facing downwards and the x direction ends up facing upwards. So we're definitely going to get a negative determinant. And once we know it's a negative determinant, what is the area? You could go through your trigonometry and find out that the area here is 3. So the area of that parallelogram is going to be 3, and it gains a negative sign because we flipped the x and y directions. There are, of course, examples in 3 dimensions as well. Maybe the 3 outputs are going to be x plus y plus z, negative x plus 2y minus 3z, and y minus z. How do I find the 3 outputs then? Let's just start in the x direction. Remember, my x vector is going to be 1, 0, 0, so I'm going to plug a 1, 0, 0, 1, 0, 0, and 0, and 0 in. So the output for x will just be 1, negative 1, 0. That's what I've drawn in over here. It's a little hard to see that that's 1 unit in the x direction and negative 1 unit in the y direction for the x vector there. And then if I want to find the image of the y vector, I'll call the y vector is 0, 1, 0. So I'm going to plug in 0, 1, 0, 0, 1, and 0, and 1, and 0. The y output will be 1, 2, 1. And so over here, this little y arrow is really in the 1, 2, 1 direction. It's pointing out toward us, even though it's kind of hard to see. Finally, in the z direction, recall the z vector is 0, 0, 1. So we're going to plug in 0, 0, 1, 0, 0, 1, and 0, 1, which will give us 1, negative 3, negative 1. And so that's what's pointing out over here. It's 1 in the x direction, negative 3 in the y direction, and then down a little bit in the z direction. But all of those are a little hard to see. If I zoom in on that image, you can see it maybe a little bit better. But now we're going to ask ourselves a question about orientation. So how is this oriented in comparison to the first unit cube, where I had an x vector in that direction, a y vector in that direction, and a z vector in this direction? Well, let's notice that going from x to z is counterclockwise. Going from z to y is also counterclockwise, and going from y to x is counterclockwise. In my output, we see, now it's a little bit tricky, but in terms of the vectors here, the red one is kind of hanging out in the back. You're going from red to blue in the counterclockwise direction, blue to green in counterclockwise, and then green to red in the counterclockwise direction. So in terms of directions, here I'm going from red to blue, here I'm going from blue to red. And so because our directionality has flipped, we're going to end up with a negative determinant from direction flip. And what is the volume of this cube? Well, it's very hard to decide just looking at it. Turns out the volume of this cube is exactly 1. So the volume ends up being equal to 1 in the output. So the overall determinant of this map will be negative 1. Finally, we have one more case of the determinant. Here my function is x minus y, y plus 2z, negative x plus 2y plus 2z. And if I look at the output in the x, y, and z directions, my x output being the vector 1, 0, 0 will go to 1, 0, 0, 0, 1, 0, 0. It looks like I have 1, 0, negative 1 as the x output. There, I've drawn it in, 1, 0, negative 1. And the y output, called the y direction, is 0, 1, 0. So I have a 0, 1, 1, 0, 0, 1, 0. Looks like my y output will be negative 1, 1, 2, which I've drawn in here. And then finally the z direction, 0, 0, 1. I'm going to plug in 0 and a 0, a 0 and a 1, and a 0 and a 0 and a 1, and I end up with 0, 2, 2. And if I plot 0, 2, 2, there it is. Now this 0, 2, 2 is kind of pointing out towards us into the screen. This, what I would want to call a parallelepiped, that's what you call three-dimensional parallelograms, parallelepipeds. So this parallelepiped here, you can't quite tell, but it's actually completely flat. Okay, it's really a two-dimensional object that kind of has this sort of hexagonal outline to it. So if you manage to look at those vectors, they all actually lie within the same plane. That's what I'll say. All 3 vectors lie in the same plane. If you've taken linear algebra before, you know that that means that they are linearly dependent on each other. And because of that, what is the volume of this three-dimensional object? The volume will end up being 0. At which point the sign, it doesn't make any sense to talk about if we've had any flips in sign, because the volume is equal to 0, and so the determinant will also have to be equal to 0. Okay, so now we've already kind of seen this proposition, which is the one I was referencing right away. If f is linear, its inverse is going to exist if and only if the determinant is non-zero. That's because it means that the volume of the image of the unit cube is non-zero. It occupies some non-zero amount of space, which means you can tile all of space with the image of the unit cube. And then similarly in matrix, the inverse will exist if and only if the determinant of the matrix is non-zero. Very important property of determinants here. Let's talk about efficiently computing them in terms of matrices, because it's one thing for me to point out what the functions look like in their pre-image and then their image. Not going to be as efficient as actually computing determinants algebraically. And so we've got a proposition that says, given a matrix, how can we compute the determinant? Well, we're going to start out for any n by n matrix, recognizing that the determinant of a 1 by 1 matrix equals its sole entry, right? So if I have a matrix here, that's just equal to 8, for example, and the determinant of the number 8 is 8. Not really a surprise. This is how much length the image of the function f of x equals 8x. This maps the unit interval, which is our one-dimensional equivalent of the unit cube. So the unit interval 0, 1 to the interval 0, 8, and so it's gained 8 times its length. That means the determinant should be 8, right? So it maps the interval to exactly its length, and so the determinant is exactly its number. Well, once you know that about one-dimensional matrices, you can find the determinant of any larger matrix by choosing any row or column, and then for each entry in that row or column, you're going to multiply the entry by the determinant of the submatrix sharing no rows or columns. What do I mean by that? Let's say I have a 3 by 3 matrix, 3, 1, 2, negative 1, 0, 1, 3, 3, negative 2. I'm going to choose any row or any column. Let's just choose the first row. And then for each entry, right, for each entry in that row, so I'm going to look at a 3, I'm going to go to the matrix which shares no rows or columns. So the submatrix that shares no rows or columns. So I'm eliminating the columns and the rows from that 3, and I'm going to go to the submatrix, and then I'm going to say determinant of the submatrix 0, 1, 3, negative 2. And this 3 that I started with will multiply that determinant. You do that for each entry, right? Each entry in the row or column that you've decided to work with. So for example, I'm going to do the same thing with the 1 here. Now what is the submatrix that shares no columns or rows with the 1? This is a submatrix negative 1, 3, 1, negative 2. And so we're going to have 1 times the determinant of the submatrix, negative 1, 1, 3, negative 2. And then there's going to be one more submatrix here. Here's the 2, the last piece. That's going to have associated submatrix, negative 1, 0, 3, 3. So I'll end up with a 2 times the determinant of the submatrix, negative 1, 0, 3, 3. So I have that from step 1. Step 1 gave me all those terms, 3 terms. Step 2 turns around and says, add each of the terms from 1 together, alternating a plus minus sign on each. So we have plus, minus, plus. And so this will be the formula that gives me the determinant of a 3 by 3 matrix, right? So that's a determinant of a 3 by 3 matrix. You might question me now and say, well, what is the determinant of each of these 2 by 2 matrices? Well, it turns out you can learn the determinant of each of the 2 by 2 matrices in the exact same manner, right? You can isolate a single row and then look at the determinant of the submatrix of the other terms and then do this alternating sign. So you work your way all the way down to the determinant of a 1 by 1 matrix. Now, there is step 3 here. If the original row or column was the jth row or column, you're going to multiply the overall result by negative 1 to the j minus 1. So in our case, the example case used the first row. So we don't multiply. Or equivalent, you can think about multiplying by the number 1, because if I put a 1 here, 1 minus 1 is 0, and negative 1 to the 0th power is just 1. Anyway, it makes more sense when you actually see this in action. So we're going to go ahead and see this in action here with the 2 by 2 determinant formula. So here we have the determinant of the matrix A, B, C, D. We're just going to go right ahead, and we are going to select the first row of this matrix. And then we are going to, for each entry in the first row, A, remove the row in the column, and we're just going to multiply it by the determinant of the submatrix, which in this case is just D. We're also going to grab the B here. We're going to isolate B, multiply it by the determinant of the submatrix C. So we'll have B times the determinant of C. And then we're going to go around with a plus minus, and then we're going to multiply everything by negative 1 to the power of, this is the first row. So because that's first row, 1. From the first, and then you always just subtract 1. And so this disappears. That's just a multiplication by 1. We have A times the determinant of D. Well, we know the determinant of a 1 by 1 matrix is itself, so we have AD, then we have a minus sign, and then we have B times the determinant of C. Determinant of C is just C. So it turns out the determinant of a 2 by 2 matrix is AD minus BC, which is going all the way back to the first thing we talked about today. We can do the same thing with a 3 by 3 matrix. Let's go ahead and isolate just the first row here. So you've isolated the first row. We're going to look at A and then the submatrix EFHI. So that's the first term I'm computing, A times the determinant of the submatrix EFHI. And then we have the middle term here, B times the submatrix DFGI. So we've got B times the determinant of DFGI. And then we have the last term here, C times its submatrix DEGH. So we have C times the determinant of DEGH. And then we're going to alternate with a plus minus plus sign, and then multiply everything by -1 to the row that we selected minus 1 power. So the row we selected is still the first row, 1 minus 1 is still 0, -1 to the 0 is still 0. So if you always select the first row, you never have to do step 3. So anyway, now we've got, A times the determinant of the 2 by 2, B times the determinant of the 2 by 2, and C times the determinant of the 2 by 2. But recall from the last case, we determined what these 2 by 2 determinants are. It's the top left. You just kind of do this little crossing action, EI. So this will be EI minus FH. This will be DI minus FG. And this will be DH minus EG. DH minus EG. So if I go ahead and distribute A, B, and C to all three of those terms, what is the 3 by 3 determinant formula? I'm just distributing A and really negative B and positive C. We end up with the determinant of the 3 by 3 matrix is AEI minus AFH minus BDI plus BFG plus CDH minus CEG. So we have one nice giant formula for the determinant of a 3 by 3 matrix. I would say most of the time we use the formulas for the 2 by 2, notably the one we just accomplished, AD minus BC, very common formula to use for a 2 by 2 matrix, as well as just taking the formula that we just discovered for the 3 by 3 matrix, AEI plus BFG plus CDH minus AFH minus BDI minus CEG. So you're going to take those two formulas and memorize them. Everything else you kind of want to use this idea of isolating a row and then selecting every single other submatrix for each entry in the row. So that's our example here. We've got a 5 by 5 matrix that we're going to calculate the determinant for by doing this nice fun with the rows. Right, we're going to isolate a single row and then use this idea of submatrices. Now, which row do we actually want to select? We want to be clever in the row we select because it turns out the row or column, right? We could select a column, but it's best to select a row or column with the most number of zeros, since this reduces computations. Why does it reduce computations at zeros? Well, zeros are going to multiply the determinant of the submatrix that is occupying the rest of space. Well, if you're multiplying something by 0, then it just becomes 0 no matter what the other determinant is. So it's definitely advantageous to select the row or column with the most zeros. In this case, we'll go ahead and select the second row. All right, so here selecting the second row, what do we actually get? Well, we have to isolate the -3, the 0, the 0, the 0, and the 0 against all of their submatrices. So in terms of the -3, the submatrix that's remaining once I remove the row and the column is here, 0, 2, -1, 2, 3, -2, 1, 1, 0, 2, 1, -1, 0, 3, 0, 0. So we're going to take that -3 and we're multiply by the determinant of that specific submatrix. Now, I have gone ahead and included all of the cases of the zeros with their submatrices, but of course, each one of those is multiplying by 0, so they all disappear. And so we really are just left with this term here. As well, I do have, this is the first case of a non-trivial very last multiplication that we need to make. Because we've selected the second row, this exponent needs to be a 2, and so we have a -1 to the 2 minus 1 power. We're going to have to make everything negative at the end. So -1 to the first power. Then we've got -3 times the determinant of its submatrix. Now we have to go through the work to find the determinant of the submatrix. So here's the submatrix. I've just gone ahead and copied it down. And we're going to do the same thing we did before with that submatrix. We're going to select either the row or the column with the most number of zeros. Here I've selected the column, first column with the most number of zeros. There's only one non-zero term. It's this 3. That means when I look at the submatrix that shares no rows or columns with this, I get the 3 by 3 submatrix given here, which is 2, -1, 2, 2, 1, -1, and 3, 0, 0. And so my term that's remaining is this one, 3 times the determinant of 2, -1, 2, 2, 1, -1, and 3, 0, 0. And because I selected the first column, I'm multiplying everything by -1 to the first power minus 1. So just multiplying everything by 1. But because of my alternating signs, there's still a negative in front of this 3 term. So we have a negative 3 times the determinant of the 3 by 3 matrix. And then we have to go ahead and determine the determinant of the 3 by 3 matrix. At this point, you could just use the formula for the 3 by 3 if you would like to. And what that gives us here is a negative 3. So we're going to end up with a negative 3 from the determinant of the 3 by 3. Well, that negative 3 will turn around. It'll multiply this negative 3. We'll end up with 9. And then we're going to take that 9. So this entire determinant is what we just decided was equal to 9. That 9 is going to multiply this 3. And we're going to get 27 as our actual determinant of this 5 by 5 matrix. So we've gone ahead and calculated that this is 27. Now it does take a lot of work to do those larger matrices. I'm not going to make you do any of those on the assignments. Just use the formulas for the 2 by 2 and the 3 by 3 on the assignment. Let's talk about eigenvalues and eigenvectors. We're not going to get too deep into the theory here. I really love the theory of eigenvalues, eigenvectors. It is actually what all of quantum mechanics is based off of. But we can't really get into the theory too much here. We're going to talk about what they are and then just look at the formula in 2 dimensions for eigenvalues and eigenvectors. So let's think about this matrix right away: 1, negative 2, negative 3, 6. And let's think about what it does maybe to 2 vectors, like 1, 1 and 2, negative 1. So if I just take this matrix, 1, negative 3, 2, 6, and act it on the vector 1, 1, it turns out the output is negative 2, 4. Meanwhile, if I take the same matrix and act it on 2, negative 1, you get the output 5, negative 10. Now, it may not seem like there's anything special about these 2 outputs, but it turns out that these 2 outputs are parallel. And that's not too terribly special about these outputs, but it does mean to say, it's starting to seem like this direction might be special, right? Because we started out with 2 distinct vectors, 1, 1 and 2, negative 1, very 2 distinct vectors. The matrix took those vectors and it mapped them to parallel vectors. Well, what would happen if I took those parallel vectors and decided to put those into the matrix? If you put either of the parallel vectors into the matrix, which the direction of the parallel vector happens to be 1, negative 2, right? That's kind of the special direction. You put that into the matrix and you get the output 7, negative 14. Let's look at that really quick. 1, negative 2 becomes 7, negative 14. That 7, negative 14 is yet again the same direction. It's like we can't avoid this direction if we keep plugging vectors into the matrix. And especially in the case here where we've put the special direction, whatever the special direction was, I'll put that in quotes, special direction. You put the special direction into the matrix, you get the special direction out of the matrix. So the matrix has some preference, right? There's some preference to these directions. And in fact, this one direction in our case. Some preference. How do we talk about the preference of the direction? Well, this 7, negative 14 really was 7 copies, right? It was a scalar multiple of 7 copies of the input direction. But the overall direction did not change, right? I think that's what the important thing is the particular direction, special direction, is still preferred. And it didn't change, but it did get 7 copies. This is what eigenvectors are. Eigenvectors correspond to preferred directions. Now, I kind of don't like the fact that we use the word vector here because it really is a direction. Vectors have both magnitudes and directions. They have lengths, right? Non-trivial lengths. But an eigenvector really doesn't care about magnitude. It just cares about direction. So an eigenvector is a preferred direction of a matrix. We can talk about what it means to be preferred by if you plug the direction in, you get the direction out. So direction in equals direction out. That's what an eigenvector is. Now, an eigenvalue is this term lambda, which is how many copies of the original the output contains. Okay, so it might be the case that we haven't changed direction, but we've gotten 10 times as long, or we've gone negative 1 times, which is in the reverse direction, but parallelness of the directions hasn't changed, or maybe you've walked twice as far, or half as far, or something like that. That's going to be the eigenvalue. So the eigenvalue is how many times our matrix has pushed us in the same direction. The eigenvector is a representation of the direction itself. So there are preferred directions of matrices. These are called eigenvectors. Eigenvalues are just these constants associated to eigenvectors, which describe how far within that direction you've moved. So let's look at an example of an eigenvector eigenvalue pair. Here's the one basically that we already introduced, 7, and then the direction is 1, negative 2. So the way we pair these up is we put the value first and the vector second, and we call these pairs. And we say that that's a pair to a specific matrix, right? These care about specific matrices. We can tell that the matrix actually treats this as an eigenvector just by acting the matrix on the vector and seeing what the output should be. So if we take this matrix on this vector, we're going to take the row, we're going to take 1 against 1 and negative 3 against 2 and add those numbers together, we get 7. We're going to take negative 2 against 1 and 6 against negative 2, and add those two numbers together, we get negative 14. Well, it turns out 7, 14 is exactly 7 copies of the eigenvector. We can do the other case here. We have 0, comma, the vector 3, 1, which says that the direction 3, 1, the direction that that vector represents, gets sent to 0 copies of itself under the same matrix, right? So this matrix 1, negative 3, 2, 6. So if I look at the matrix 1, negative 3, 2, 6, and I acted on the vector 3, 1, I'm going to take 1 times 3 plus negative 3 times 1, you end up with 0, and then you take negative 2 times 3 plus 6 times 1, you also end up with 0. 0, 0 happens to be 0 copies of the original direction. And so eigenvector, eigenvalue pairs, you have eigenvalues, how many copies, eigenvectors in what direction. And then they're always assigned to a specific matrix because the matrix kind of has these preferred directions, eigenvalues and eigenvector directions. One more example in a 3 by 3 case. There's nothing special about the 2 by 2 case. So in a 3 by 3 case, we've got the eigenvalue negative 5 and the eigenvector negative 3, 2, 6 associated in the matrix 3, 0, 4, 0, 4, negative 3, 4, 0, negative 3. What does it mean for this to be an eigenvector of eigenvalue negative 5 associated to this matrix? Well, we're just going to say what it means is that if I take that vector negative 3, 2, 6 and I perform matrix multiplication, what's this going to end up being? Well, it'd be 3 times negative 3 plus 0 times 2 plus 4 times 6 in the first row. It'll be 0 times negative 3 plus 4 times 2 plus negative 3 times 6 in the second row. And it'll end up being 4 times negative 3 plus 0 times 2 plus negative 3 times 6 in the third row. What you're going to get out of this is 15 and then negative 10 and then negative 30. But wait a minute, 15, negative 10, and negative 30 is exactly negative 5 copies of the vector you started with. And so the direction is still preferred, and it turns out we've got negative 5 copies of that vector. There's another one for a different matrix and another one for a different matrix. So all sorts of examples of these which you can explore if you would like to. I'm just going to talk now about the specific eigenvalue eigenvector pairs that you can find for 2 by 2 matrices. These are the only ones that will show up in our version of multivariable calculus. We're going to restrict ourselves to 2 dimensions when these show up. It turns out that there are 25 dimensional equivalents of this, or 300 dimensional equivalents, or whatever number of dimensions you want to be in. There's the equivalent of eigenvector eigenvalue pairs. It's just not something that we can actually delve into for now. In fact, in infinite dimensions it works too. So anyway, how do we find these, right? Because we've talked about all of them. How do we find them? At least in the case of 2 by 2 matrix, what you do is you take your 2 by 2 matrix A, B, C, D, and then you assign 2 numbers to this matrix. You assign the number capital T and the number capital D. You've already seen the number capital D. We've been analyzing it all class. This is the determinant. The number capital T is called the trace. Okay, so the trace is just A plus D. The trace is the sum of the diagonal entries. The determinant we've already encountered today. Now it turns out you can use the values of the trace and the determinant alone in the 2 by 2 setting to find all of the eigenvectors and eigenvalues. So you're first going to find eigenvalues by calling lambda plus minus. It's the trace over 2 plus minus the square root of the trace over 2 squared minus d. This looks like a quadratic formula because the quadratic formula is hiding behind this. You can ask me in office hours if you would like to see why. But you have this thing called the 2 eigenvalues, which are just determined, this subscript plus assigned to that plus, and then the subscript minus I assigned to this minus. So there really are 2 eigenvalues, depending on if you choose a plus or a minus. And then you can find the eigenvectors dependent on the eigenvalues. Now it will be down to a couple cases. It depends on if, the cases depend on if these values b or c are non-zero. But in the event that b is non-zero, then your first eigenvector, which I call x plus, this is the one associated to the eigenvalue lambda plus, that eigenvector will be the vector b and then lambda plus minus a. And then the second eigenvector, x sub minus, this is associated to lambda minus, will be the vector b lambda minus minus a. So they're going to be your 2 vectors in the case of b not equal to 0. In the case that c is not equal to 0, you can do something similar. It turns out x plus will be lambda plus minus d in the first entry and c in the second entry, and then x minus will be lambda minus minus d in the first entry and c in the second entry. In the event that both b is 0 and c is 0, you have to get a little bit special. It turns out that your eigenvalues are just a and d, and the eigenvectors are just the unit vectors, so 1, 0, and 0, 1. And that makes a lot of sense if you think about the only cases where both b and c are 0 are when you have a, 0, 0, d. And this matrix, this linear map, is just going to scale x by an amount a. That's what this represents, the 1 in the x direction by an amount a. And it's going to scale y by some amount in the d direction. So there's your y entry, and it gets scaled by d. So those are all of your cases. It's maybe a fairly chunky proposition, but really not too hard to implement, very plug and chug when you want to do it. Let's just look at one example of computing the eigenvalue-eigenvector pair for a 2 by 2 matrix. So we can find the eigenvalue-eigenvector pairs for this matrix 1, 2, 3, 0 by choosing a, b, c, and d out of it. And we're going to immediately recognize that, in fact, both b and c are non-zero, so we could have used either case 1 or 2. They're going to give the same equivalent. If we want to compute the trace here, remember the trace is the sum of a and d, so the trace is 1. And then the determinant is, of course, a times d minus b times c, so that'll be 0 minus 6. It'll be negative 6 for the determinant. We're then going to just use the formula given right here. Trace over 2 plus or minus root trace over 2 squared minus the determinant. We determined our trace was 1 and our determinant was negative 6. And so we'll have trace over 2, which is 1/2, plus or minus the trace over 2 squared minus the determinant. The determinant was negative 6. Now we're just going to evaluate everything out. 1/2 plus or minus root 1/4 plus 6. Well, 6 happens to be 24/4, so we get 25/4 in the square root. 25 has square root 5, 4 has square root 2, so we get 1/2 plus or minus 5/2, meaning if we choose the plus half of plus or minus 1/2 plus 5/2, the 6/2 is 3, that's our first eigenvalue, or if we choose the minus half, 1/2 minus 5/2 is negative 4/2, which is negative 2. As I said before, because both b and c are 0, we can use either of case 1 or case 2. They will still provide eigenvectors, no matter which one we choose. We're just going to go ahead for fun and choose case 2. So case 2 is saying x plus is lambda plus minus d over c, and x minus is lambda minus minus d and c. So we'll choose case 2 here. We can choose case 2. Here is lambda plus minus d, and then the entry in c. So even though we have 2 3's, one of the 3's is lambda plus and the other 3 is c. And then x minus will be lambda minus, which we decided was negative 2, minus d, and the second entry will still be c. So our two eigenvectors are 3 times negative 1, 1, and negative 2 times 3. It turns out that scalars, like this 3 here, won't play a big role in directions, right? They don't represent directions. So you can always drop the scalars if you want. I just call that eigenvector negative 1, 1. And then our second case in the eigenvector-eigenvalue pair, negative 2, 3. So those are the eigenvector-eigenvalue pairs of that matrix. One more example here, but I'm not going to go through it. It's hanging out in the book if you want to see it. Anyway, that is all of linear algebra as far as I wanted to introduce it to you. Sorry we went through eigenvalues and eigenvectors a little quickly. Think about them as preferred directions in matrices. They're directions that matrices won't change. They may make them larger or smaller, but they don't change these directions. And then we have a formula on how to find those. Anyway, I'll see you in the next one. We're finally getting back into derivatives. See you then. Bye.